Let me get started. Welcome everyone to our DSG seminar. I'd like to, as always, start by thanking SAP for sponsoring this speaker series. It's my great pleasure to introduce Professor Thomas Haigh. Today is a very different seminar because, pretty much every seminars we have a database researcher who comes and says how his database is or her database is 10x faster than the previous database. But today we are hosting actually a CS historian. Thomas is a CS historian. He's a professor and chair of the history department at University of Wisconsin-Milwaukee. And although he is a historian, he did study computer science at University of Manchester, which is a historic place. This is where Alan Turing spent 6 years designing the first stored program computers. But then, according to my conversation with him today's breakfast, by some kind of accident, he ended up in history of computer science and did a Ph.D. at UPenn. And he writes a lot about different sort of topics within the history of computer science, from the history of databases, the internet, operating systems, and most of his work is on AI. He's authored many books, so I'll just tell you several of those books. A New History of Modern Computing, ENIAC in Action, and his upcoming book, Artificial Intelligence, The History of a Brand. But I know him and his work through the articles he wrote on the history of databases. So if you've ever taken a graduate course with me, the first lecture is always an article by Thomas on the history of databases. So some of my favorite articles are Where the Data Got Its Base is a great article. Another one is A Veritable Bucket of Facts, essentially telling the stories of 1960s and 70s at the birth of the field. And sort of those are some of my favorite articles in the entire database field. So today he's going to also talk about history of databases. Tomorrow he has a second seminar on the history of AI. It will be at the same hour, but next room, 1304. Okay, so with that, I'd like to thank him. By the way, so I should maybe stress this. So I did not know Thomas. I just sent him a cold email, so I want to thank him especially for making the trip all the way here, taking the flight, and spending 2 days with us, even though he didn't know me in person. So I'm very grateful, and I'll leave the floor to Thomas. Thank you very much.
Thanks. Oh, well, thank you, and I'm very glad to be invited, particularly to talk about database history. So I've been getting a relatively large number of invitations to talk about the history of AI, because like everything in the world is AI these days. The database things I worked on mostly early in my career, although I've retained an interest in the area, and it's a relatively obscure topic, so it's great to be here, and also that there are so many people in the room to hear about database history. So what I'll be saying in this talk mostly overlaps with those articles that you mentioned, although it's going to be extending it a little bit and into talking about data warehousing, and also talking about what the history of database management systems might be and how that's different from the history of data, which is something that historians of science have been getting excited about lately. So that's the structure of the talk. So those first 3 bits are telling the story from the 60s and 70s, where the database management system comes from. The 4th bit is going to talk a little bit about how relational systems are different in some ways, but not as different as you might think, is what I'm going to claim. And then the database management system history versus data history thing that I mentioned. And if you've heard, to be honest, I haven't looked at data at recent editions of textbooks. So at least textbooks always used to start out with something about the relational model and the network model and how the relational model was better. And I hope they haven't completely gotten rid of that bit at the beginning. So the history I'm giving here mostly is what comes before that, or what kind of complicates just that idea that network models had been around forever and they were bad, and then the relational model was good. So the first of those 3 pieces, talking about file management software and where data files come from. So computers were first applied to business pretty soon after being invented. So this is, I think, the first glossy ad for a computer in business. You see the management type people there inside the vacuum tube with the desk, which is pretty cool because they were emphasizing this technology is electronic, it moves at amazing speed, and the UNIVAC was the first computer promoted for that purpose. By the end of the 50s, hundreds of American companies had ordered computers and begun to apply them to their routine business tasks, particularly payroll, accounting, invoicing, and so on. And in most of those areas, punch card machines, which were electromechanical, were already in use. So in many cases, they weren't going straight from paper records to computer tapes. They were going from punch card, data that was already on punch cards, but being processed manually with punch card machines, which was a whole separate genre of technology. And it was a fairly incremental process. So on a tech level, electronic computers are revolutionary. But I've argued that on the organizational level, the technology is mostly applied conservatively as an extension of what was happening with the existing non-electronic punch card machines, automating clerical work. So the claims being made were, we can displace enough people doing the clerical work manually that we can pay for the cost of the computer by saving on payroll clerks, which turned out not to work. But that was the kind of mindset that a lot of companies were buying computers with in the 1950s and early 1960s. So they migrated. You may wonder why a file is called a file, right? Because a file, literally like a file of soldiers, it's a bunch of things lined up in order. The answer is, in this context, well, it comes from paper files, but it also comes from punch cards, which were arranged in decks, kind of in a sequential kind of way. So actually, a lot of data terminology doesn't even come from computers. It's carried over from that earlier punch card machine era. So they're migrating the master files from card decks to reels of magnetic tape, and everything in mainstream business computing in the 50s and early 60s is about effective batch processing of large numbers of records stored sequentially on tape. So application programmers are working directly with the record formats used on the tape. The IBM mainframes that are sold for business use have got substantial hardware support for this. So they've got basically subsidiary processors doing the input and output, helping to read records from tape, because they're optimized for those kinds of business applications. COBOL, the first widely used high-level language for business, is also all about working with structured records stored on tape. So during this era, spinning tape drives really symbolized computing. So if any of you have seen The Italian Job, the entire plot centers on smuggling a roll of tape into the traffic light control center in Turin for their shiny new computer-controlled traffic system, so that it can shut down the city and the thieves can make their daring getaway with a bunch of gold in a fleet of minis. And in James Bond films and so on too, it's like spinning tape drives, because that's the only bit of the computer that really moves, like symbolizes like high-tech computer centers during the period. There's the actual University of Georgia tape drives in the 70s, and that's the vault where they kept the tapes themselves. So anything involving large volumes of data is all about tape during this period. And of course, tape is sequential. So this is an example from a publication in the period, 1962, of a manufacturing control system. So a business application at this point would not be one program that runs once. It would be a whole suite of programs, each of which you load in input tapes, you load output tapes, you've got a master tape that gets updated on a batch basis, you've got intermediate tapes, you could have up to 8 tape drives on one computer, and the operators are always loading and unloading tapes. So you can just see the number of little tape symbols here for different intermediary steps. And again, all of this is just one application, but look at the number of different runs, the number of different tapes. So as things are first computerized, it's about doing these kind of routine, heavily tape-based things. Now, the problem we've got there is, even if you've got master tapes somewhere that give a, for example, here's the master tool file on this diagram. So you periodically run an update, you batch things, you copy the old master file to the new master file, make the updates as it goes by. But all the information, and this is a bad thing from the manager viewpoint, is locked up in those tape files. If you want to query it, you can't go and look at it like you could do with paper things. You need to work with the programming team. And that means writing a program to pull the information that you want out of the file. And program time is scarce, and maybe they never get around to you. So you probably have to figure it out yourself by going through gigantic stacks of printout that might be delivered weekly by forklift truck. and work it out for yourself. So it didn't take people long to realize that it would be nice to have a generalized set of subroutines that could work with, maybe update, definitely query and maintain the files for reporting purposes. That idea is basically its old as corporate computing. It's first documented in General Electric in the 1950s. And if you just have a generalized report generation system, and you feed it the metadata that describes the format of the specific file, and maybe a manager checks off some boxes for what fields that they want in the output, and totals and subtotals, that gets punched onto a card. You feed those into the report program generation system. It spits out a program, you execute that, and you get the report that you want. And for efficiency, you could wait till you've got several reports that need to be done for the same file, and the software could make multiple reports on one run through of the tape, because everything is about optimizing the amount of work that you get out of the computer by doing as much as possible each time you pass a tape through it. And by the 60s, they're getting more sophisticated. So products like this are actually the foundation, in large part, of the beginning of the independent software industry. There's a package called Mark IV from Informatics, which is the first software ever to hit the $1 million and $10 million sales milestones. And other things. So that's what's happening kind of down there in the trenches of business computing. Then we've got a different historical trend, and that makes file management and report generation packages, tape-oriented. Then on the kind of high-end science fiction, cutting-edge side of things, you've got people dreaming of doing integrated things in real time. So hard drives first come along in the 50s with the specialized system IBM RAMAC, which you query by putting cards in. And the idea is you can keep, say, your inventory up to date on the hard drive and ask questions and get the latest responses. So you can run transactions individually. It starts out as with a special purpose card-oriented computer, the RAMAC, but pretty quickly they're available for other systems. And you begin to get the concept of a database. So the OED has the first known usage of the term database in this context, 1962, from the System Development Corporation. They produced a very ambitious networked computer air defense system called SAGE in the 50s and 60s. And they had the contract to do the software development for it. Within SAGE itself, it seems like the tool was compool. So you've got all these sensors and missiles and bases and so on coming into these blockhouse SAGE computer centers, which themselves are networked between centers. There's a whole bunch of them. Within each blockhouse, you've got this enormous computer, actually two computers, duplex for reliability, that fill an entire floor. Physically, I think the largest computer ever mass-produced. Extremely important, very prominent system in the history of computing. And what they have there, actually, is the idea of a compool. So you've got different information coming from different things in real time over different kinds of network links, and it all needs to be assimilated to give a single coherent view that shows up on these very early video displays that are basically adapted from radar scopes. So you see here at the bottom, right, they don't quite have hard drives yet, but they do have drums, which are very expensive, but this is a money, no object kind of system. So they do have the random access storage system there to try and keep a coherent view of data in real time that is coming in from all these different subsystems and driving the display system. And SDC in the 60s begins to seek out civilian applications for similar technology. So it tries to commercialize. It actually gets into information retrieval as something it thinks is going to be a big industry with online systems because it's got unique expertise in programming online and time-sharing systems coming out from these kind of projects. And it doesn't do very well in commercializing. But this is the kind of context where people start talking about databases, particularly as something in a product category. In the late 60s also, there's an enthusiasm for the idea that managers, right, that these kind of military-inspired, screen-driven, network, real-time systems are something that can also be applied to business. So consultants start trying to pitch these kind of somewhat Star Trek-inspired ideas, particularly with this control panel here that's supposed to call up different views from this is just a mock-up. I don't think anyone ever made anything like that work. But if you've seen the original Star Trek, it might look reasonably familiar. And the pitch that, if we can just get managers the information they need, the managing is going to take care of itself. But the only reason that managing is stressful or difficult is because we don't have enough information. And this ties in with the idea of the management information system. So I've got a whole paper on this, inventing information systems, also from early in my career. And it's something that gets originated at the very end of the 50s, but through the 60s, the management information system is kind of the hottest idea in business computing. Consultants are pitching it, computer companies, etc. And the idea is with more powerful computers, online access, and hard drives, we can make something that is basically a real-time, enterprise-wide integrated system that is, in modern terms, some kind of mashup of SAP and a data warehouse with added simulation and modeling capabilities. Which is completely unrealistic in the tech of the time. But people go out and try and build these things, and obviously they don't work. So this is a pitch from UNIVAC, and they're saying, here's your big, hard-to-manage company, but they're just saying, with a UNIVAC total management information system, management is no longer the remote apex of a pyramid, the hub of a wheel. Every activity is monitored on an absolutely current basis. Centralized control of decentralized operations become a reality painlessly. So there's even this idea to sell mainframes that can, again, 100% not deliver on this promise. But those ideas do come together. And the earliest use I found of it actually goes all the way back to 1959. So they're not quite talking about a database yet, but this is where I got that title, Veritable Buckets of Facts. At the very beginning, when they first start talking about management information systems, they say to make this work, you need a body of data, a veritable bucket of facts, as the source into which information-seeking ladles of different sizes and shapes are thrust in different locations. So it's more of a data soup at that point. But you get the idea there. And they talk also about pools of data, data hub, data bank. And it seems like it's the mid-60s where database becomes the agreed-on term for this thing. Well, they were starting out just with a soup-sized thing, but no, now you need a whole lake full. And you get this idea. This is from actually a guy who worked on Sage, Robert V. Head. So this is kind of literally the idea of the database as the base on which other kinds of systems fit. So at the base, you're integrating all the different operational systems so that they can share data with each other. And then that's the basis on which you erect control and planning systems as a kind of hierarchy. And this information pyramid becomes a complete cliche in like the 90s and early 2000s. So here's an example from a 2000s, right? So that idea goes all the way through, at least into the 21st century, the information pyramid. So the state of play around 1967 is we've got these two different streams. On the database side, it's an idea that's fashionable. It's widely promoted as the key to delivering on the management information system vision. It's revolutionary, but it's also vaporware. And so is the idea of a real-time, online, totally integrated system. In the world of technology that actually exists, we've got file management systems, which are a growth area, the foundation of the beginnings of the software industry, batch-oriented, tape-based, practical, but not particularly exciting. And if you look at those two things, we've got the database and we've got the management system, but they're two different things at this point. So as you might expect, the next bit of the talk is about how those things get put together to make the idea of the database management system. And we're going to go back in time a little bit for this to look at something that is basically the technological core of the database management system, but wasn't originally called one. And that is the integrated data store proposed in 1962 by Charles W. Bachman of General Electric, goes on to win the Turing Award, the first non-academic to win a Turing Award, and possibly still the only one without a Ph.D. So that's a recognition of the kind of the size of that accomplishment, that he was an early winner of the award. Yeah, I'd have to think more about that, but certainly one of a very few. Maybe Floyd never got a PhD, or maybe he never got an undergrad. Actually, yeah, I'd have to check back, but it's certainly like a very small group, and those are both like enormous engineering type accomplishments. And it's definitely outside the normal run of Turing Award winners. So the idea there is it comes out of basically a management information system type project, because General Electric is it prides itself on its modern management and its tech and its efficiency. They've got their own internal business school at this point. They've got their own systems teams. So he's part of a corporate level staff system team that is supposed to be figuring out a modern integrated computerized piece of software to help run factories. And GE hopes that it can roll this out across a bunch of different factories in different parts of the business. And they realize that the only way, you can't just go and develop an application and try and make that work, that they have to invent a whole new technology for this to work, which is the integrated data store. And that is a level of system software that sits between the application programs and the hard drive. Because like everything programmers know how to do is all about sequential stuff on tape. Now, obviously, you can just put your sequential file on a hard drive and read through it to find the record that you want, but that is completely wasting the entire point of random access. But, well, you guys, probably know this, right? But the techniques that you need to use to efficiently index and find records on a disk are so much more complicated than what you needed with sequential tape. Most programmers can't cope with them, most application programmers at this point. And even if they can, reinventing that for every application doesn't make sense, especially as the applications all have to coexist on the same hard drive. So he figured out you need to have this thing that mediates between all the application programs and all the records, and explicitly codes connections between different record types, which is the only way that you're going to get this integration of data between applications that people are so excited about. It's based around General Electric's prototype disk drive. And you'll see a couple things there. So there's the random access idea. You've got 1 million pigeonholes for records on the hard drive. How do you obtain the record that you're interested in? You also see here the idea of chains of records, and they also have the idea there of links that go between different record types, say, from customers to orders, those kinds of classic things, in a very flexible kind of way. So how it's initially implemented is it takes over the entire computer. There's no operating system. This is the operating system. And in fact, the users submit job cards with data updates and what they want to run. And the system itself stores those in essentially what we now call database tables. So it's even managing its own job queue using its native data structures, which is something that doesn't translate into the commercial version. It's an interesting thing about the original concept. And at this point, they have only 8,000 words of memory, 20 bits each, right? So that's about 20 kilobytes of memory. And they managed to get the problem controller and the rest of IDS into about half of that, leaving the rest for the programs to run and do their business, which, it's a pretty amazing feat of efficient memory usage. So it's got the basic capabilities that you'd expect, like retrieving, updating, modifying, deleting records. There isn't originally a data definition language. It's punched straight onto separate punch cards. But you do have the idea that you can update or what we'd think of as being tables. They have their own terminology. It's all record sets and so on. It's not quite the modern terminology, but the concepts are there. But you can update the data structures and you don't break the applications, which is crucial and one of the big benefits of this, because otherwise everything becomes an unmaintainable nightmare if applications are going directly against the hard drive. And then that is commercialized within a couple of years. So they add some features like recovering transactions if the computer crashes partway through, support for COBOL programs, and GE is offering this as a commercial product from the mid-60s. It's bundled with its computers. The problem is not many people buy GE computers, but there was a clone of it, IDMS, for the widely used IBM family computers that becomes an extremely important software package in the 70s.
So is IDS the first commercial release, or is IDMS the first?
It all depends what you mean by DBMS. So I'm going to argue this wasn't called the DBMS at the time, and it's missing some features that are seen as being crucial for a DBMS, particularly the ad hoc querying interface. So the ad hoc querying is being handled by report generation packages, and in fact they add expansions for those to run against database type systems, as well as sequential tape files, because that's not something that early DBMS-like systems are good at. So I don't feel 100% comfortable calling this the first DBMS, but I do call it definitely the system from which DBMSs evolve.
So, in what sense are you thinking about transactions and recovery at this point? Is it formalized, or is it some loose way of going back in time?
Yeah, so this is before the formalization with ACID, obviously, which is a whole separate thing. What they do have is essentially a tape that is used to journal what's happening. So if the power goes out or the computer crashes, after it's debited and before it's credited, the classic transaction type thing, then when you restart it, it's going to go back to that tape and make sure that both parts that have to happen together have happened together. And if it doesn't, it will unwind them.
So some rudimentary and rudimentary wrong.
Yeah, it's mostly intended just to guard against, I think, power failures and crashes. But it's something that they recognize even back then is essential for something that's going to be deployed by banks and in these kind of mission critical applications.
I'm kind of curious what you mean by clone. Do you mean stolen? Do you mean deliberately re-engineered?
So the B.F. Goodrich Chemical Company had got some people who really wanted IDS, but they couldn't because the company was standardizing on IBM software. So they produced what was essentially a re-implementation of the same capabilities internally. Then it was recognized that this was of something that was of interest, and it became Cullinan. So there was one of the highest flying database companies of the 80s and I guess late 70s was Cullinan. Bachman finished up going to work for them as a consultant. So I think that maybe it's an employee. So they kind of paid him back with a job. But it started out as an IDS clone, but because the 360 systems were so much more widely deployed, it was much more widely used than GE's IDS ever was.
I guess we didn't have software patents at that point.
Well, that's a whole kind of separate legal history. There was a software patent early on from ADR for the autoflow system, I think was the first one, but it was one of those legal gray areas for a long time. So I don't think GE patented any of this. So where do we get to the database management system? Well, 1968-ish, Codicil, the industry group that had standardized COBOL previously, knows it needs to do something for this modern world of data storing systems and hard drives. So it wants to do some extensions. It produces the database task group. Bachman himself plays a major role in steering this. It adopts a lot of core concepts from IDS. But it essentially says, what you need to have is something like IDS with the capabilities for programmers, plus real-time operation, as well as batch operation, plus the ability to query directly. So those are the checklists that are formalized the idea of what a database management system should do. And so you've got that kind of idea of different interfaces for programmers and for managers. The data definition as being a language, which wasn't quite there in the original IDS. And Bachman follows up with another group, ANSI Spark, which I think he also chairs, which comes up with it tries to do a bunch of stuff, but what it leaves the world with is the concept of program and data independence, which are also there in IDS. So these systems set up explicit links between record types. So there are other systems that are just purely hierarchical parent-child relationships. This is the network model, as it's later called, so you can have these kind of arbitrary graph-like connections between things, but they are explicitly coded there in the data definition language and reflected in the physical format for efficiency. Also, the records themselves are rigidly standardized and formatted. So as Bachman puts this in his Turing Award lecture, it's like the Copernican revolution where you realize that the sun doesn't revolve around the earth and it's the other way around. So in this case, going from the idea of everything is about doing things to data as it flows through the computer memory to the idea that the programmer is navigating through structures of data in their applications, turning the programmer into a mobile navigator who's able to probe and traverse a database at will. Okay, sidebar. There's also efforts to diagram these kinds of relationships between things, most notably with entity relationship model in the 70s. And I'm just working on my book about AI at the moment, and it's really interesting that very similar diagrams are appearing in AI at about the same point to try and represent, like, is-a relationships and knowledge in a structured way. So there's something going on in the 70s with the idea of representing various things as essentially structured graphs. So in the 70s, the DBMS is really important for application programmers. It makes their lives a lot easier. It makes application development faster. Maintenance becomes possible, which it wouldn't be if you had to re-implement every application, every time you change, add a few fields to a table, etc. But there's also a bit of a narrowing. So in the 70s, database had been this broad, free-floating kind of idea. And then we get the effective redefinition of databases, something that's managed with a database management system, which is about these regular record types. So it's not great for anything like full text, ad hoc linkages between records, context. So information retrieval kind of branches out as a different thing, which had been more tightly the database concept in the 60s. And we reached the point where actually a lot of the time people say database when they mean database management system. You've got that kind of slippage between the things. Yeah?
In those terms, like what programming languages they use to develop these systems? C or?
Well, the systems are developed in assembler at this point. I mean, they have to be with that tightness. The application programmers, the original IDS, they would have used a high-level language that was GE custom. For efficiency, they then go over to making the application programmers use assembly language with the data operations called as macros. And then they add support for COBOL later on as that becomes established as a dominant language. But I think the systems themselves are written in assembly, as most things are in this period. And the hopes for the integrated management information system are reborn with the database. So database administrator starts out as this kind of management idea about a high-level person who's going to take charge of treating data as a resource, much broader than machine-readable data, according to a 1974 article, be something of a superstar, and it's going to be bringing this idea of a single, enterprise-wide schema back on track, which obviously is not how the DBMS finishes up. And the idea of building a single integrated company-wide operational database actually turns out still not to be workable, right? You finish with a whole bunch of different databases fragmented. So it's a lot better than if people were still, using files for everything. So the dreams of integrated systems eventually get realized with essentially the combination of data warehousing and ERP. ERP integrating on the application level, data warehousing giving you reporting capabilities from that. Now, how do I think relational fits in with all this? So this is probably where awareness of database management history usually starts, if you've got that little bit at the beginning of the textbook. So of course, Edgar F. Codd of IBM Research proposed the relational model in 1970. He also wins a Turing Award. It's elegant, it's flexible, it's minimalist. There's a lot of questions at the beginning about whether it's actually implementable. There's a famous debate with Bachman at an ACM event in 1974, which I'm going to write another piece in CACM about, where the two sides basically argue past each other. Bachman is all about, we've got these giant industrial systems that are all about doing massive amounts of transactions very efficiently. The academic people are talking about the joys of the relational model. The workability of the relational approach is established a couple of years later when IBM System R becomes operational, at least on a demo basis. Also introduces the SQL querying language. IBM commercializes that in the 80s, and then DB2 comes along. And there's also Ingress at the University of California, Berkeley, which is another crucial early implementation. As Don Chamberlain said later, SQL actually started out with this dream of being the end-user querying language that would be so easy managers could use it, and it finishes up being the standard way that application programmers do their data operations. So that also didn't quite finish up as being used as they expected. But the shift to RDBMS for new applications is pretty gradual. Now, one of the things I want to say is you can't imagine a relational database management system unless the idea of the database management system is already there. And I think sometimes when people look at this history, they kind of take the DBMS concept for granted and only see the weaknesses of the network system. But in fact, the database management system concept was pretty new and also had to be invented. I think maybe Bachman's importance in setting that up sometimes gets a bit overlooked. Also, although academic people tend not to see the systems that are out there in the world, the transition to relational systems was slow and incomplete. So the codicil type network systems, following Bachman's model, remained dominant on mainframes and were very efficient in high volume transactions. I think RDBMS really had a lot of growth with the shift to mini computer and Unix-based systems, was what gave that an opportunity for companies like Sybase and Oracle and Ingress.
I would disagree with your last point.
As far as I know, at least from Canadian companies, IMS still makes the world go round.
IMS still?
Makes the world go round.
Yeah.
Every major Canadian bank, every major Canadian insurance company, all of their major record-keeping systems are using IBM's IMS, and we still are. IBM is still making $1 billion in revenue every year on IMS licenses.
Oh, all right. So you want me to say codicil/hierarchical?
Well, they're not the same, but
Very different.
Anyway,
Arguments all the time about those.
I will absolutely say that. But what I meant there is they're not relational, right?
They're not- yes, they're not-
That's what I mean there.
absolutely true.
Like, we think of this as something that is a long time ago, but it isn't, is the point of that sentence. Yes, sure.
IMS, in corporations, IMS was way more popular than any IBMS system.
Yeah, all right, so, yeah, I could fix that. But I think in the bigger picture, we're agreeing with each other that they didn't throw all that stuff out and re-implement with Oracle.
No. Yeah.
And even now.
Even now. Yeah.
How
You
would
go,
you-
you go to an ATM, it's talking to an IMS system on the back end.
Yeah, because like, why are they going to throw all that away? And also, you know, they don't need that flexibility. They've got a particular kind of transaction that just needs to run in massive volumes. Now, relational database management system, and I'm oversimplifying here as well, but you all know, right? The big thing that everyone got beat into them is normalize, like higher normal forms, store each piece of information only once, join the tables together at runtime to put things back together, which makes updates very easy. It also makes a lot of querying kind of very slow, particularly if you've got to combine information from a lot of tables, or you need to aggregate and count information stored from a large number of records. So that's why you need data warehouses. And that explicitly is the idea that you're not going to be able to integrate everything into a highly normalized operational system that is used by everything. So you leave the transactional system spread out and make a read-only copy of the data that's updated regularly in a data warehouse, which needs to be loaded, restructured, etc. So that was like a huge thing in the 90s and early 2000s. That's like a picture of kind of how that stuff, you know, is coming in from different systems, being summarized, being queried. So loading data is a huge thing because the information is not all stored in consistent formats, so it needs to be converted, standardized. Duplicate and inconsistent data is going to be like an enormous thing. So that's just an example of kind of how that is functionally eventually solved, but also how far practice didn't go with the dream of having everything run operationally off a consistent database. So the data often is stored in a star schema, which is also for efficient aggregating and querying versus efficient updating in the operational systems. I seem to have lost a slide that I thought I was going to be here. Okay, I'm just going to say what I wanted to say there then, and then I'm going to go through the conclusions. So what I wanted to say there is, in practice, as relational systems evolve, they kind of converge in some ways with network systems. So the dream is, the join is going to be specified in the query. It's not there in the data definition language, the relationships between tables. But one thing is people care about coherence. So real-world relational products get referential integrity constraints put into the system so that you can't have something that's a child record if there's no parent record for it and so on. They get enforced at runtime. And that's bringing you back towards the more hardwired connections of the network model. Another thing is, my experience in the 90s was, in practice, any kind of query that you actually want to run, you need to have an index to support it. So the only queries that are usable at any kind of scale have got indexes there, and maybe you have to put hints in as well to get the thing to work it. Things may be better now, but the experience then was, so you actually have to put the indexes in to reflect the joins that you actually want to make. And another thing is, end user querying systems, the dream of SQL being used by end users doesn't so much happen, so you get these visual querying systems, and they've all got the joins hardwired. So you drag and drop the tables in the fields that you want, and the joins just show up. So as well as not being as normalized as the dream was in practical systems, actually a lot of that putting the connections between tables into the data definition language comes back in practice to make relational systems usable on a commercial basis. All right.
So the dream of SQL being used by non-programmers, were there any kind of serious products that tried to do that? Like, I think when you say that, what I'm imagining is like you typing in text,
Well,
like a natural language question kind of.
I think IBM's first commercialization of SQL wasn't DB2, it was SQL/DS, and I think the DS was decision support. So the idea was that, like, if not managers, then at least like staff analysts working for managers, because it's in reporting stuff that flexibility would pay off more than in transactional stuff. So it kind of made sense,
But
but
the DS was only in the name.
yeah.
SQL DS didn't actually do any of that. But IBM first shipped what they called Query Management Facility, QMF, in the 1986 timeframe. And that was designed to be given to a manager to say, here you go, you can actually write up your own queries in QMF.
And that's more like English? Like what is that?
Yeah, it had some similarities to SQL. It also had some English keywords in it. Complete failure.
Yeah.
Certainly in Great West Life, none of the managers could actually make heads or tails of how to write a QMF query to get them what they really wanted. And so they just ship it back to the application development area anyway and say, hey, you do this.
Yeah.
I can't figure it out.
I mean, the pitch they made for SQL is kind of the same as the pitch for COBOL, that managers should be able to understand it, because if you read through it, it all makes sense in English, allegedly. But it doesn't. I mean, it's like a syntactic sugar, but this, like, thinking in relational terms. With students, there's always that kind of hill that they're climbing, and some of them never quite get it, and then like something clicks and suddenly like, oh, it makes sense now. But expecting managers to do that just because you've got an English-like syntax. And of course, like, Dayton Cod never liked SQL because it imposed some limitations on what things that you couldn't say in SQL that you could say in relational algebra. Okay.
I think
2 points. One is that Cod himself was quite critical of SQL, especially what we now call SQL databases, where they went from set-oriented to bag-oriented semantics and some other stuff. And he wrote and talked extensively about it until it was the late part of his life. The second is that Cod himself worked on a natural language interface to databases. Google the title, 7 Steps to Rendezvous, and you will get a report of his attempt to design a natural language interface, which failed because the iterative work with users was quite a number of steps before the system could understand what the user was asking.
But I want to kind of second that. So the rendezvous system that Code worked on, there is a scenario of an interaction with the system in natural language, and it's really impressive that they were able to do that in 1970s.
All right, so I'll just offer a couple of conclusions, then we can go back to the questions and discussion. Right, so why care about this? Well, one reason is, while databases might not be the most glamorous thing in computing, they're absolutely one of the most important. I mean, just fundamentally important system software for pretty much everything, because they underpin all the applications, all the websites, everything that anybody is doing with computers. There's a DBMS underneath it. And most people don't know that. They just see the application. They never think about where the data goes. And that includes a lot of scholars. Like, I'm involved with a media studies group in Germany, and they've got really excited about sensors, and everything in media, that piece of media studies is sensors, sensors, sensors. And they never think about, like, where does the data go? And I'm saying, wait, maybe we should be thinking about databases as well, right? I mean, how can you, take all that sensor data, but you need to structure it, and what you can do with it depends on how it's stored, etc. From the viewpoint of the business history of computing, these packages are absolutely crucial to the early software industry, and of course, Oracle is still, pretty damn important company. Right, the websites, you finish up with MySQL as part of the core LAMP stack that is driving everything. So I recently did this big overview history of computing book with Paul Ceruzzi as a replacement for his classic History of Modern Computing. And where could I squeeze database management and database history into that big structure? So what we had there is, the idea is each chapter, the computer becomes something different. So you start out with ENIAC, you finish up with like computers being everything and used by everybody all over the world to do most of the stuff that they do. That's a pretty difficult story to tell structurally. So what came up with it, each chapter is the computer becomes something new. So as you can imagine, there's a lot of databases and the computer becomes a data processing device. But we found other places in the story to put it too. So we put the DBase and OEP systems in chapter 8 on the computer becomes office equipment. We talked about relational DBMSs and client server in chapter 10. The PC becomes a mini computer. That's the 90s and the shift from like DOS to NT, which is really a next generation DEC operating system, functionally speaking. And then the cloud-based tech and so on with the move to cloud-based web applications in the computer becomes a network. So we talked about that kind of shift too, and also the LAMP and MyPHP stuff. So we did try and find some ways to like try and alert the broader world that actually databases are pretty important for all this stuff. But as a scholarly field, even within the history of computing, DBMS history is mostly still missing in action. I've written a few papers. There have been a couple special issues of IEEE Annals of the History of Computing focused on the business stories of network hierarchical and relational database management system companies. There is something happening in the history of science, which is a somewhat separate field from the history of technology and business, which I identify with, that historians of science and mathematics are right now getting excited about data history. So I think with big data, but also data sounds scientific, right? It sounds like something that the history of science should be caring about. Historians of science talk a lot about epistemology and ways of knowing, and they've got a strong tradition of talking about quantification and statistics. So they're coming at data history from that viewpoint. Unfortunately, they're largely ignoring database management systems. So to give an example of this, a recent popular trade press book written by Matt Jones, who is now a professor at Columbia, and Chris Wiggins, who is, he moved to Princeton, sorry. And Chris Wiggins, who I think is also the data director for the New York Times. So sweeping history of data and its technical, political, and ethical impact on our world. This was when big data was the thing. Jones did say to me, if we just called it AI, we'd have sold 10 times as many copies. So it's like how quickly those brandings are moving. But remember, big data 5 years ago was the big thing. And it's a good history. They've done it nicely. They start out with statistics. They talk about AI, World War II, machine learning, science of data. They talk about all the ethics and racism and web advertising and algorithms and stuff. But there's some stuff they don't talk about. And I know Jones knows about this stuff, and asked him why, and he said, the editors just wouldn't let us put it in the book. They said, no, it would put everybody off. So some terms not found in this book, the history of how data happened. Database management system, COD, Bachman, right? No hits. Because it goes with that kind of statistical, thinking about data in those statistical terms, and of course DBMS systems primarily about storing, updating, and retrieving individual operational records, and then you can put the extra stuff on top to analyze it statistically. Statistical data sets are fundamentally flat tables. There's not that idea of the links between them. So if you come at this from a history of science and statistics viewpoint, you don't really see the importance of database management systems as technologies and infrastructures. And I wish kind of more people would pay attention to that stuff. Because I think a lesson from this story, right, thinking about just the struggles. Corporations had computerized a lot of their data, even in the 50s, but being able to actually pull out the information and do things with it, took essentially another 50 years to realize that dream of having the data integrated and queryable in a comprehensive kind of way. So what an organization or individual can do doesn't depend so much on the data that they have, or on how fast the computer is, or on how much storage they've got. It depends on the capabilities of the software that is mediating their access with that data, i.e. a database management system. Application programs themselves are not dealing directly with the data. Since the 70s, they've been going through some kind of DBMS. So what you can do with data doesn't just depend on this kind of stuff, but it also depends fundamentally on the affordances of the database management system package to use its basic approach, the methods used to structure the data, and the way it's stored, to the extent to which, like even if you're using Oracle, you might have the data stored in a completely different way for a transactional system versus a data warehousing type system. So Also, like even in computer science now, I mean, when I look at syllabi for database courses, it seems like Berkeley, and maybe you teach it this way here, they still expected, at least last time I looked, students to go under the hood and know what's really happening and how the data's being stored and how the DBMS systems work. But certainly most places, students learn how to use SQL, and they don't learn very much about like what's going on under the hood in a DBMS. So almost nobody at this point, I think, knows what's actually going on inside these systems and where those crucial affordances that are driving what's possible to do with computer applications matter, right? So any DBMS is going to make some things easy and other things hard. There's always going to be trade-offs, there's always going to be different approaches, e.g. with those classic distinctions of hierarchical network and relationship. So there's no neutral or optimal way to structure data that is going to be optimal for like every application, for every purpose. To some of you that might sound really obvious, but I'm not convinced the broader world really understands it. And that's the end.
Questions? So, near the start, you're saying sometime in the 60s, if I understood correctly, IR kind of separated from DB. That question makes sense.
Yeah.
Could you comment? I mean, are these coming together again now? What's your thoughts on IR and/or versus or whatever DB?
Yeah, so that kind of went with SDC as it tried to move from these military systems to commercializing. So their idea was this would be some kind of online system that people with teletypes would use as end users to put their data into a time-sharing system and query it how they want. From that online time-sharing system, you've got systems like Dialog and LexisNexis that become big in the 70s that go off and do their own thing, and that becomes a completely separate history from the DBMS history, and they're not using, I think, database management packages. And DBMS as it develops is very good at these kind of structured, regular data files that you're accessing with keys, and it's not good at full text, context, irregularly structured records, which becomes a separate thing. I mean, in the present day, you guys would know more about that than me. I know people have found ways to do a lot of things with relational systems. I also know that people have been pushing alternative models for different things and cloud data and so on. I mean, Google and of course LLMs are their own thing, and that's all anyone wants to talk about these days. I mean, in a way, LLMs are information retrieval too, right? So I honestly don't have a clear sense of how all that plays out in the present day. I think people have found ways to do a lot of things with relational systems by extending them in maybe kind of clunky ways that work practically but steer away from that kind of original core sense of what they're about.
So the development of these systems sounds like it's driven by this to integrate everything.
Yeah, I would say, functionally speaking, basically three things. People, right, so if a company has they've computerized their payroll system, they've computerized their order processing system, they've computerized their bill of materials, where they go from, we need to like build a big thing like an aeroplane, to all the thousands of components that you'll need at certain dates to have delivered so that people can make the sub-assemblies that's all going to be integrated into the big system at the end. And they want data to be able to flow between those things. You don't want to be manually rekeying data from one to the other. So if a customer has ordered something, it would be great if you could take all the orders and have that automatically drive the materials processing, which is going to work with the production scheduling system, and then workers are going to be working on something and they need to get paid. So instead of having the same information duplicated in different formats in different tape-based systems, you want it all integrated so that the information is flowing beautifully from one piece of the business to another with one integrated view of data.
So that would be an economic reason that it's more efficient, integration is more efficient and they would make more money. Is that a historical reason for the guys to integrate, or what would you say the historical reason for
Yeah, I mean, there's operational efficiencies there, but there's also the idea that the problem was computers were so expensive Everything cost more than they expected. It went obsolete faster, and they needed way more programmers than they expected. So the idea of justifying the cost of computerizing by saving money on file clerks, didn't really work. So they needed another way to justify it. And what they said is, computerization is not really about saving money on administrative stuff. It's about, doing things better and faster, but it's mostly about the business benefits that come from turning your information into a strategic resource. So you want to be able to query and assemble and model and have the business make better decisions on the strength of being able to do stuff with the information that's locked up in the tape files. So that's where the integrated management information system was not just an idea about saving money operationally, but it was primarily a justification that the real benefit of computerization is going to come from executives making better decisions. And to do that, you need to have all the information integrated and cross-referenced.
Do you think the rise of the NoSQL, they call NoSQL databases like graph databases, document-oriented, they came long before the ideas, but is it the data model that is motivating what should be the database management system, or is it the opposite?
I see it as there's some central ideas for database management systems, like they're going to mediate all the accesses between users and data. They're going to have interfaces for ad hoc querying and for application programming. They're going to be robust and fault tolerant and do transactions. They're going to give data and program independence. And that actually applies across all three of the traditional data models. So those aren't just ideas for relational database management systems, those are ideas for database management systems as a whole. So extending that, I don't have any personal experience with NoSQL, cloud-based type things. But I think any of those systems, you're going to want to keep at least some of those general properties of a database management system. Certainly you aren't going to want to have data structured in a way that is deeply dependent on a specific application, which would be the case if you didn't have a database management system and application programs were maintaining their own files directly.
So you have spent time with Charles Bachman.
Yes.
And, kind of following up on the previous question, when you sort of look at this history, and also I'm curious about what you sense from Bachman, we sort of interpret this history as that there was a debate between the relational model and the network model, and then the relational model took over. It's the most widely adopted sort of data model and class of database management. Did you get a sense that Charlie Bachman, do you think that that was inevitable, or do you kind of interpret this history as a set of accidents, and did you think, did you get a sense from Charlie Bachman kind of appreciating relational systems and that they had some better interfaces, etc.?
Yeah.
Or could it have turned out differently? I'm curious if you look at this history and say this was inevitable, this was the better idea, or do you say it was a mix of sort of accidents?
Well, as you know, when I met Bachman, he was retired, but still using Microsoft Access to put together a schema for a database for a company that was banking cord blood that he was a consultant to, which was kind of fascinating to see it. So he clearly, had come around to using and understanding how relational systems worked. I think he was coming so much from the engineering mindset and knew that on the business side, the practical benefits of having efficient, high volume, robust transaction processing were really compelling. And on a system of this size with 8,000 words of memory, there's no way they could have started out in 1962 with something like the relational model. So what they had with the idea of giving programs some independence from how data was structured and sparing application programmers from having to try and learn these very difficult, very specialized techniques for efficient random access storage. In some ways, there was a lot more that was uniting relational and network systems, I think, at this point, with the shared idea of a database management system versus what was dividing them. The relational approach did have some real benefits, but I mean, again, from the fact that IDMS and IDS and other old school systems are still what are running the highest transaction processing systems in the world. Like, it's not that there's ever a one-size-fits-all kind of solution. Updating and flexibly querying is much easier with the relational systems. Efficient, high-volume, routine transactions is still a genuine strength of the other kinds of systems. I did see in Bartman's papers, which are deposited at the Babbage Institute, that he was on the Turing Award selection committee, and he didn't give COD very many points when they were voting on who should be the nominee. So I think maybe he did, at least in the 70s, kind of feel that sense of rivalry there, and that maybe the relational people weren't as appreciative as they should be of the real-world industrial concerns and the strengths of the network-based systems. But I think in the big picture, it probably is inevitable that the trade-offs that are appropriate for an environment like this are not going to be the same trade-offs that are appropriate when you've got computers that are thousands of times more powerful. And I haven't used a big-scale Oracle system in like 20 plus years. Maybe you don't have to index everything now. Maybe it all works beautifully just like it's supposed to. But even in the 90s, I found in practice, you couldn't just give the query you wanted and expect it to run fast enough to use on a production basis.
If there's any question, one more question we can take.
I noticed the book, you gave the table of contents for that book, and it reminded me a lot of a quote from Douglas Adams about what people thought computers were. Was that in your head, or did you... Actually, I pulled it up if you want to hear it.
All right, I'll hear that one.
Yeah, he said, first we thought the PC was a calculator, then we found out how to turn numbers into letters with ASCII, then we thought it was a typewriter, then we discovered graphics, and we thought it was a television. And with the World Wide Web, we realized it's a brochure.
That's a nice quote. No, I hadn't come across that one. And of course, it's not just the PC, which is what he'd be personally familiar with. That's in some ways like recapitulating the history of computing. But the media stuff definitely is PC specific. Yeah, and it makes it really hard to write the book, because in the first chapter, you've got things that are one-off laboratory pieces of equipment, kind of like cyclotrons, millions of dollars, only a few hundred people in the world ever use them for scientific number crunching. And then as you go through, it becomes all these different things until, it's kind of become everything, but it never stops being the old stuff. So you don't want to give the impression, well, computers used to be about like large-scale record keeping and administrative process, because of course they still are, even though most people never see like where the bank is doing its back-end processing or whatever. But the scale and the structure and the kinds of people that you're dealing with, where in the beginning it's very specialized technical communities, later on it's ordinary people, trying to encapsulate the history of computing in one kind of book is just a real engineering kind of challenge in figuring out how do you even structure the thing and still have it be liftable.
Great. So there will be a student meeting at the DST lab at 3:30, and let's thank Thomas again.